Okay, let's start, all right? So, let me see, all right, today I plan to finish seeing the data, right, the seeing the t-statistic. Ideally, according to using decision theory, that we should ideally want to make our decision such that our decision is based on the probability of the now conditional on the data. So the example I gave last time is, and also said that if you want to interpret p-value this way, you can interpret p-value as the probability of the now being true based only on the observed data set, right? In other words, discard all the prior knowledge. If we have any prior knowledge, we do not consider them. So the understanding of p-value is, you can think about the p-value as the probability of H0 being true only based on the observed data set, without incorporating any prior knowledge. And when I say that, it's actually, what I'm saying is essentially the key difference between the so-called frequentist approach and the Bayesian approach. So for people of you who have heard about the Bayesian approach and the frequentist, the key idea, the key difference between the two is that frequentist approach draw conclusions only from the data you have at hand, while the Bayesian approach essentially tries to incorporate prior knowledge. Okay? Now, I'm not saying that Bayesian approach is the better approach, because in theory, if we could incorporate prior knowledge, of course it'd be better. But in practice, prior knowledge is subjective, so it's very hard to actually have a consensus prior knowledge. So when you do Bayesian analysis, the biggest problem is often how do we actually specify any prior that people can actually agree on. So that's a huge limitation to Bayesian practice, right? So in practice, people use, there are many people who are strictly frequentists, there are many people who are strictly Bayesian, and there are many people who use both, depending on the applications. Where that battle between frequentist and Bayesian is largely not a battle today. It used to be a fierce battle, not so much a battle today, because we realize that each practice has its own limitations. The point I want to make in this lecture is that when you think about p-value, right, it's beneficial to think about it in terms of this Bayesian framework, where ideally we want the probability, the posterior probability of H0. Okay? But instead, our decision when we do hypothesis testing is based on a p-value, which is something that without incorporating the prior knowledge. Again, just repeating myself from last time, right? We have this example of coin flips. If I flip the coin 1,000 times, and 500 times its head, 500 times its tail, and suppose that's my history, okay? That's my prior knowledge. And then I do a new experiment. In this new experiment, I flip the coin twice, and both times its head. So if you incorporate the prior knowledge, you would look at this new experiment and say, okay, we got 2 more heads, but considering all the history, I would still say this coin is most likely to be unbiased. But if you draw a conclusion only from this new data set of 2 flips, then you would say it's most likely to be a biased coin. And to do hypothesis testing based on p-value is more like, or you could say the frequentist approach is more like drawing conclusion only based on this new data set without incorporating the prior knowledge. Right? So that's the analogy I gave last time. So today we're going to talk about some other frequent issues that happen with doing research and publish based on significant p-values. The idea is that if we only focus on significant effects, okay, statistically significant results, then it's very likely that the results that we see in published studies are going to overstate or understate the true effects that we have. So let me give you a very simple example. Suppose we have a beta hat, and it's an estimate of the underlying true beta star. Right? So this beta hat is unbiased. So basically a normal distribution around the beta star. Okay? So the true beta star, our estimator is normally distributed around the true values. It's an unbiased estimator. However, right, if we only consider statistically significant results, so you can imagine that we have this estimator, right? And this estimator, every time we draw some data sets out from the underlying population, we use the estimator and it gives us a beta hat. So on average, it is unbiased. Okay? It is a good estimator, it's unbiased. However, if we only consider the statistically significant results, then that means we will only consider beta hat whose value is larger, absolute value is larger than 1.96 if we use the 5%, right? Everybody agree? It's a normal 0, 1, right? So if it's normal 0, 1, if we know that's a normal 0, 1, then statistical significance at the 5% level means that we'll only accept or reject the null if the beta hat absolute value is larger than 1.96 or 2 in this case. Okay? So let's just make it simple. So if we only consider beta hat that is larger than 2, then the average value of beta hat conditional on beta hat larger than 2 is clearly an overestimate of the true beta star. Everybody agree? Now, let's do a sort of a simulation to show you this point. Right? Suppose I do this simulation where x is just a 0, 1 variable, and the y has this linear relation with x. It's 1 plus 0.1x, and a normal distribution around that. Okay? So y essentially is equal to 1 plus 0, 1.x plus e, and this e is a normal 0, 1. That's our setup. So in this case, the alpha, the true value is 1, and the true value of beta star here is 0.1. Okay? All right, so what I'm going to do is I'm going to draw 100 samples from the underlying distribution. I'm going to generate 100 samples. And in each sample, there's going to be 200 data points. Okay? And every time after I draw the sample out, it's like if I draw the sample out, I'm going to run a linear regression on that sample using this formula, right? Using this linear regression beta 1x plus e. I'm going to do this on every sample. And so I generate 100 samples. So from those 100 samples, I am going to get something like that, right? Okay, so every different sample has a different beta hat, because every time when I draw the sample out, I estimate a beta hat. The beta hat is going to be different. Okay? Right. All right. Now, so I get a lot of beta around 0. I got some beta above 0.2. I got some beta below negative 0.2. Okay? So in other words, I got some beta hat that is absolute value is a little bit larger, and most beta hat is clustered in the middle. If you do hypothesis testing, then all these middle beta here was going to be statistically insignificant. Only these green ones are going to be significant, right? So now this is another way to plot it. Okay, so we do this 100 times, and we get 100 different beta hat. So if we look at their distribution, then essentially we can draw them this way. I'm sorry, not distribution, right? This is p-value, and this is beta hat. So we plot p-value versus beta hat, we see a lot of beta hats with very large p-values. Only this extreme beta hat has very small p-values. Now, imagine that only these beta hats will be published by journals, because journal will only accept statistically significant results. Then what you get is, what you see in published study are extreme values rather than the true unbiased estimator. Okay? That's called a publication bias. And I have a number of examples here that you can go through, right? We can change different, but the key insight here is that if we only accept statistical significant results, then our average estimate of beta hat is going to be larger. It's going to be overestimated of the true beta star in our case. All right, so what does that mean, right? That means in many cases when you read, first of all, right, suppose you're a reader of research. You read a lot of research published in journals that says something like, let's imagine some cases that not in economics, right? Oftentimes you read research published in medical journals, for example, that says this new drug or this new way of life, maybe drinking green tea early in the morning, that study finds that drinking green tea increases our life expectancy by, how many years. And the result is statistically significant. Okay? And whenever you read results like that, you should always be suspicious that there may be many studies that also do green tea on life expectancy that do not find any results. and they're not published. And only the ones that get published are the ones that find really truly extreme effect, right? Like the beta hat we see here, okay? Like the beta hat, like these beta hat. So, which means that when you are reading these research, you should always in your expectation, adjust the true significance of the results, because the results may not really be that significant. There are so many unpublished studies. And that is really an unfortunate situation, right? Because as an industry in publication, we have to have some standard or have some criteria about what results are interesting to publish. And oftentimes the reliance on p-value and on statistical significance will lead to this kind of situation. Okay. So here are some morals from this story. Whenever you read research, you should always assume that the magnitude may be exaggerated, right? Because a lot of small magnitude studies are not published, and you should adjust your belief accordingly. And the second is when you can always collect new data to replicate published findings. It's always good practice to do replications, and that is a huge issue in a lot of natural science and medical studies, which is because people think that these studies, published studies, may overstate. So it's always a good practice to replicate them. Now in economics, we don't quite do replications. You find very few people spending a lot of time to replicate economic studies. Part of the reason is because in economics, if you do replication, it's kind of useless. You cannot publish your results. Again, this is the industry, right? The third thing is if you are writing a paper, if you're doing your own research, the advice is really don't easily throw away results that are simply because they're insignificant. Right? Okay. And finally, when you're reviewing other people's paper, the hope is you do not judge a paper only because it has delivered the so-called significant results. Okay? You should always look at the merit of the paper, the design, the methodology, the data, and what the results say, even if they are insignificant. Right? That's the hope. All right, the second kind of problem is very related to this publication bias, is the idea that because journals, typically the standard for publication is that your results has to be significant. That's why people spend a lot of time trying very hard to get significant results. So this is called in search of statistical significance, right? So people are desperately searching for significance, and that can lead to a lot of problems. So the best practice for data analysis, after we finish our foundation lecture, I hope you already understand right now. The best practice is to fix your model before you see the data. So before you come to the data, you already have an idea what model you are going to use. That's, if you do that, then your results have better generalization ability. Okay? So I hope you all understand that after our talk on foundations and regression. If you and then you should always keep a separate data set to test performance, right? Test data to really assess the performance of your estimate model. Okay. In practice, that's not always doable. So many researchers will try many specifications or models after seeing the data, and then until they reach their desired statistically significant results. So, and sometimes even, so this is one thing that people typically do, which is bad. Another thing that people typically often do, which is also very bad, and even harder to detect, is that people will change the data. Okay? It's not so much that they are intentionally to fake data. No, we're not talking about faking data. We're talking about you can process your data in different ways, such that you get significant results. So I'll give you some examples later. Okay. All right. So that brings us to a famous dictum by Ronald Coase, which is if you torture the data long enough, it will confess. Right? So if you try hard enough, eventually you'll get something significant. And such practice, sometimes called data-dependent analysis, but it's not a very good word, but such practice is often called p-hacking or data snooping. Right? In the sense that people are trying until they reach their conclusion after seeing data. So this is torturing, right? So you can torture the data until the data confess. So like I said before, last time, when you do this, when you try and try and try until you reach a satisfactory conclusion, in the end, your product essentially is a hypothesis that is picked from the union of all the hypotheses, of all the models you have tried during this process. So in the end, you have a huge VC, a very large VC dimension, and the result is going to generalize very bad. Intuitively, whenever you are trying very hard to fit, right? You're trying very hard to find a good result. It's like trying very hard to fit the training data. If you try too hard, your result is not going to generalize, right? It's the same idea we have talked before. Okay? Now, let's talk about a specific sort of manifestation of that problem, which is called multiple testing. Okay. The idea of multiple testing is you have a data set, and you want to run a regression. And in the regression, you have to do a hypothesis test, right? So test whether beta is significant or not. And you would test it. If it's insignificant, you would run another specification and do the test again and see if it's significant or not. You do this until you reach significance. So that's multiple testing, okay? Or specification search, or multiple testing until you reach your desired conclusion. So now let's think about what that means, okay? If I have y equal to, well, I'll just give you, let's just assume a model, right? So I'm going to run one test. In this test, let me just say is test null hypothesis number 1, and you're going to test null hypothesis number 2, and you will test null hypothesis, let's say n, okay? The n hypothesis you're going to test. And you are going to find, suppose you pick n hypotheses to run, and then you find one of them significant. Okay? The other insignificant. And you're only going to, say, publish this one, right? Send this to the journal. Okay? So the question is, if you test n hypotheses, what is the probability that you will ever find one that is significant? Now let me just assume, okay? Assume that each null has a, okay, so assume that each null is true, okay? Every null is true. So in theory, we should accept all the nulls, okay? Every null is true. Now, if every null is true, if you just do one test, what is the probability? And suppose we do suppose you reject a null if p-value is smaller than 0.1, okay? Suppose. Now, if you only do one test, what is the probability that you falsely reject the null, or you falsely accept the alternative? If you only do one test. If you only do one test, what is the probability that you have a wrong conclusion? 5%, very good, okay? Right? Because this 5, what is this? This is the 5, this is essentially, when you say you want a p-value to be smaller than 5%, right? You're saying that, look, 5% of the time, we'll see a sort of a very extreme value of this type, right? So 5% of the time, we'll make a mistake. We declare we accept H1 instead of H0. Okay, so now 5% is a pretty small number. So that's what we are happy with, all right? We will take the risk of having 5% error. What if we have n hypotheses? We test n hypotheses at the same time. And now each one of them is true, so we should not reject, we should accept all of them, right? But if we test n of them at the same time, and let's assume they're all independent, then what is the probability that you will find at least one that is significant? Okay? Or, that's similar to the coin flip story we did in our foundation, right? Now, it's very easy. It's basically 1 minus 1 alpha to the n and 1 minus this, right? So this is the probability that none of them is ever significant, and 1 minus them is at least one of them is significant. And this, of course, is larger, often much larger than the true alpha, right? So we end up having a much higher probability of finding something that is significant. Right? So the more you test, the higher the probability you will find something that is significant. It's a very easy idea. In fact, let's look at this very interesting, very nice little Do what? Okay, so so this is one page that says, okay, let's do 100 tests, and in each test we will reject at a percentage at 5%, right? Okay, now sorry. Yeah. Okay, so let's do it. Okay, test, right? Now, in theory, for this test, with the 100 test, in the underlying 100 hypothesis, nothing, every null hypothesis is true, okay? Every null hypothesis is true. We should not reject anything. Everything should be insignificant. But you try them enough, it's insignificant, significant, right? Publish. Insignificant, significant, publish, significant, publish. It's if you try enough, you will get significant results, which you can send for publication. Right? So very. In fact, we have this relationship, right? If you try once, the false positiveness, the probability of you falsely rejecting the null is 5%. If you do it twice, it's 10%. It's almost 10%. Do it 5 times, it's 20%. If you do it 100 times, then 99%, almost with certainty, that you will always find something that is significant. This is assuming independence of the test. Okay. So that is called multiple testing. And I'm going to show another example, just to not to belabor the point, but just another nice example to show this at work. So suppose I have draw 100 data points from the following distribution. Now Y is just a uniform distribution, and I draw something called a male. Okay, just a random variable. It's called a male, and it's a 0, 1 variable. And also let me draw some X variable, and this is called treatment. Okay. You can think about an X variable, it's also 0, 1. And you can see that these 3 variables have no relation with each other. They're all independent, right? However, I'm going to run a regression. I'm going to run a regression of Y on treatment. Now, they have no relation with each other, so we should not see anything, right? So indeed, the treatment is insignificant, right? Okay, so that's good. But that's not good for me because I want to have something significant for publication purposes. So I don't like this. So what I'm going to do is I'm going to run a regression of Y on treatment, but only on male, okay? So I'm going to run this regression only with male individuals, not with female individuals. So let's see. Subset, right? I only look at the subset where it is male. And let me run the regression, and I get significant treatment. Just by chance, right? In fact, this is just by chance. But, I could, if I get the result, and of course I can also run female. If I run female, then it's not significant again. Okay? So the point is, simply by dividing the data into male and female, I get something significant for the male. And what can I do later? I can tell a very nice story that there is this effect. I do this experiment, and this experiment, like drinking green tea, whatever, right? So the drinking green tea, like I published results saying drinking green tea has significant health effect on male. It helps the guys, but doesn't help the woman. And I can tell a lot of stories about why that's the case, right? Because woman is already healthy enough or whatever, right? Okay, so you can always do that. And that's a very typical case of specification search. And in fact, the cartoon here, this is XKCD cartoon, very famous cartoon that depicts exactly the story I was just telling, where there are some grad students doing research, or scientists, right, doing research on whether there's a causal link between jelly bean and acne. Okay, so whether eating jelly beans will cause acne. So this guy says we found no link between jelly bean and acne. It's not significant, right? Okay, so we cannot publish. But wait a minute, we can do more, right? So there's no link between jelly bean and acne, but we can test whether there's a link between gray jelly bean and acne, or or green jelly bean, right, or red jelly bean or black jelly bean. Let's just split jelly bean into different colors and test each color. And in the end, we find that for green jelly bean, it's significant. Okay, so we have a study that says green jelly bean cause acne, right? That's exactly the story I was talking about, right? News, green jelly beans, linked to acne, okay? This happens more than you think in reality. Right? There's a lot of study like that actually gets published in the as a result of process like this. And this is another famous, not famous, but this is a very interesting study, which the author, right, they wrote a study that says neural correlates of interspecies perspective taking the post-mortem Atlantic salmon. Okay, so the idea for this one is the salmon, it brain scan the different parts of the brain of salmon. And then it can say that the, hold on, let me, I kind of forget what the study is actually about. I think this study is that they put salmon in they let salmon watch some TV. I forgot, okay? So I have to double check. But they let salmon watch on TV or listen to some news or whatever. And they brain scan the salmon. And they find out that that some areas in salmon's brain has statistically significant reaction, okay, activity. Because the brain has, right? So the brain has random neurons firing, and in some cases statistically significant. So they find these regions that significantly respond to news or TV. That's my recollection. I have to go back to check. Now, that's obviously impossible. So the author says that is impossible, not only because it's implausible that salmon can ever respond to news or whatever, right? It could respond. Maybe it could respond to images. It's impossible because the salmons are dead. So the authors are using dead salmon for this study. So it's completely impossible. So why do we still have statistical significance here? Because we are doing multiple testing. The author actually did, right? There are 130,000 different vortices in the brain you can test. If you test all of them, that's a huge multiple testing. And eventually you'll find some random chance that you'll get significance. Okay? So the author wrote this article just for fun, right? To show that if you do multiple testing, it could lead to a lot of problems, right? So that was very nice. But enough with the sort of a fake study and the cartoons. Let's look at some actual study. And so this is a study, ovulation and voting, published by Psychological Science. And so the title is, right, so this is actually funny. So the title is The Fluctuating Female Vote, Politics, Religion, and the Ovulatory Cycle. The author study whether when women are in different periods of their ovulatory cycle, that will impact on who they vote. So specifically to look at women during the 2012 US election, whether they vote for Obama or Romney. And the idea is that if a woman is in the, what is the conclusion? I think the conclusion is if a woman is ovulating, they would vote for Obama. And if they're not, they would vote for Romney, something like that, okay? So let me see. Ovulation, yes. Ovulation led single woman only. So ovulation led single woman to become more liberal and voting for Barack Obama. And if you're married, then you are more likely to vote for Mitt Romney. So we all know that Barack Obama at the time was a handsome and young and promising politicians. Why do you have that face? You don't think Obama was a handsome guy at the time? Anyway, so this is a study that essentially says, look, the ovulation and the biological behavior can affect a woman's voting behavior. Now, of course, that could be offensive to many people because that's assuming that women cannot vote rationally. They're impacted by somehow this hormonal response. But disregard of politics, right? Let's look at how this study is actually done. So here is the description of the method and the data. It says we sample 275 women with a mean age of, let's say, 28 years. And what they're doing is they pick women with regular cycle between 25 and 35 days, and then they divide this woman into several groups. Okay, they call it high fertility group, which is this amount of cycle days, 7 and 14, and low fertility group. And for our main analysis, we do not include women on cycle days 15 and 16. We also do not include women at the beginning of the ovulatory cycle. or at the end of every cycle. So that's a long description of how they pick their sample, and then they divide the sample. They define the variable fertility, right? High fertility, low fertility, and also they define relationship status. So they say participants who indicate they were engaged, living with a partner or married, were classified as being in a committed relationship. Otherwise, we say they are not in a. We say they're single. Okay, all right. So it looks like the description of. So right now the author said this is how they process the data, and they define high fertility, low fertility. They also define single and not single. Okay, and then they're going to run their regression using these variables. Now it all looks very normal, but if you think about it, right, once you think about it, why do they actually define relationship as being why do they count people who are engaged and living with a partner and married? Why do they put these people together in one group and put single in another group? Because for a lot of people, the natural way to divide according to like marriage status is that they're going to divide people into married and not married, right? Okay? So for many people who do analysis, they say, okay, you are either married or not married. Here they put married together with living with a partner and engaged, and then they put single on the other one. So maybe that's understandable, but again, this choice is interesting. And here, why do they exclude a woman at the beginning or at the end? Okay? And why do they divide the cycle into a high and a low fertility according to this particular criteria, which is not universal? So all these things all these choices kind of seemed interesting, right? So here is what the Andrew Gellman did. Right? So this came from Andrew Gellman. Andrew Gellman looked at this paper. He didn't believe it, the results. So he went and he asked for the data, and the author actually gave the data to him. It's very nice. And he rerun the whole analysis, but just changing the definitions a little bit. Okay? So changing how we define fertility, changing how we define relationship, right? And then changing the process of data. Specifically, he changed the way that data is defined into variables, and then changed the way the sample is defined into many different possibilities. Okay, we have 4 different possibilities for fertility. We have 3 different possibilities to define cycle, and we have 3 different possibilities of defining relationship. So altogether, there are, according to him, he used 108 different possibilities. Okay, different ways of defining variables and processing the data, and he tried all 168 different specifications, and this is the result. Okay, so here, what we have is the confidence intervals, right? And so this is confidence interval. And this is 168 different combinations, different way of processing the data. And this is the author's specification. Okay? So you can see that of 168 different specifications, how many are truly significant? Only one here, and one here. Probably only 3, maybe 4 are truly significant, right? For every other results, the confidence interval includes the 0, okay, the null. So he tried 168, and only 3 or 4 or 5 are significant. All the other ways of processing data, they're all insignificant. So what does this say about the reliability of the previous result, right? Now, of course, we should be, Andrew Gellman was very clear that he was careful to say that the authors, he did not believe the author intentionally did what they did. Maybe the intentional, maybe not intentional, we don't know. But at least if you try all these different possibilities of defining variables, you quickly find that the previous result was not very reliable. And it could just be a result of specification search. Okay? Right. So that's why, for example, he really advocates that whenever you are doing research yourself, and you truly want your result to be to be robust, to be reliable, then you should do something like this, right? Try many specifications, and see whether your results stand. Okay, change your definition a little bit, change your sampling method a little bit, and try different specifications and see how robust it is. And indeed, so this is a nice comeback or reply to the previous paper. So remember, the previous paper did women and their hormonal, ovulatory cycles for the 2012 election between Romney and Obama, right? So these people did the same research when it comes to the, let me see, which director, Probably not this research. Let me see. But anyway, there is a later research, okay? I have to find, but there's a later research that used the 2016 election and did the same study. And of course, the effect between late cycle and political voting disappeared. Right? So again, that's just showing you that these kind of research may not be very reliable. Okay. Now, how do we deal with this problem? Okay, it's not completely hopeless. One of the things that people say you can do is to do the so-called Baroni correction. Now, the Baroni correction, as we'll see, is a very strong correction. So in practice, people do not really use them. But this is at least, let's talk about them and how, what the idea is. The Baroni correction is very simple. If you're only doing one hypothesis test, you can reject it at the 5% level. So if your p-value is smaller than 0.05, let's reject it, right? Now, if you're doing many hypotheses, if you're doing n of them, then you should reject your results or accept the alternative if the probability, right? If the probability of any one of them being significant is less than 0.05. Okay, that's a very simple idea, right? Because this is like if you try n, if your goal is to try n of them and you'll publish, or at least you get one of them that's significant, then you should really reject, or you should really do that only if this entire thing, right, this whole probability of at least one of them being significant is smaller than 5%. Only in that case should you accept the so-called alternative. Okay, and of course there's a simpler way to write it, because we can just, a rule of thumb is that we can just reject. So if we want this to be true, then we should reject each now at a probability not alpha, but alpha divided by n. If we do this, then the so-called family-wide probability will be smaller than 0.5, right? Because 1 over alpha divided by n and 1 minus, okay, will be smaller or equal to alpha. Okay, that's it. Now, so what this Baroni correction implies is that if you are doing 10 hypothesis tests, then you should reject each one at the threshold not of 5%, but should 5 divided by 10, okay, 0.5%. In other words, you should make it much harder to reject each individual hypothesis so that your family-wide error rate is contained, okay? Now, this is a very strong correction because it's essentially assuming that each test is independent. In reality, our tests are not independent, so this is in many cases, the overkill. Okay, but if you want to really guarantee that you're not harmed by multiple testing, your results are not harmed by multiple testing, then Baroni correction will be one way to do it, and to convince the reader that you're actually being serious about specification search. Okay, now specification search is just one example of data snooping. So now I want to talk more generally about data snooping itself. Okay, the whole idea of data snooping is that if your data has been affected by any step in the learning process, then it cannot be truly trusted in assessing the outcome. This is a very general principle. It's also the principle that underlies our division of data into training and testing. Right? So if you're training your data on the training set, do not assess how good your model is on the training set. Assess how good your model is on the test data set. Because why? Because the test data set has never been used before. The training set has already been used. And if it has already been used, then your results is already specifically optimized for that data set. Right? I hope that's understandable. If it has already been used, then the model is already picked with the specific purpose of fitting those data points. So it's not going to tell you the true story about how it's going to perform in the underlying population. Right? So that's a general principle. Anytime your data set has been used in picking out the final hypothesis, it's somewhat contaminated. And it's better to use a separate test data to confirm how good it is. Right? So that's the principle. Now, that has a couple implications, right? It says if you choose a model based on the data set, if you look at the data set and you choose a model specifically to fit that data set, we all know that your final hypothesis will actually perform worse because you have a large VC dimension, right? Now, if your approach try a series of models before finally picking one, then the effective VC dimension is not the final model, is the union of all the models. So we have already talked about this point. Sometimes it's very hard to, however, sometimes it's very hard to avoid that. Because even if you're not consciously doing model 1, 2, 3 and picking one, okay? Sometimes this process is not conscious. Because sometimes you just look at the data. Okay, so let's look at this data. Now suppose I want to find a function to separate the blue and the red. Okay, right? Because the red is maybe +1 and blue is -1 or 0, 1 variables. We want to find a function that helps us separate those two, predict whether it's red or whether it's blue. If you don't look at the data and you want to choose a model, what model do you choose? Maybe you choose a linear one, maybe you choose some other models, but as long as you look at the data, you'll quickly realize that the linear model is not going to work for this one. You'll quickly see that, look, something like this is probably a better model. So without even trying the linear model, you will begin with a non-linear model. Because you look at the data, you know the linear model doesn't work. That's called eye test. And that's what people often do, right? People do all this time. You get it, you take your data, you plot it, you look at what the data looks like, and you decide, hey, what model I want to use. So in this case, you are not consciously trying model 1, model 2, model 3. You're unconsciously, or at least you're using your eye test. But does that mean your final result is good? No, because in your eye, you have already tried the linear model. So in the end, your VC dimension is the combination of this non-linear model and the linear model, because you have already eyed it, right? It's a really simple idea. Now, when I say this, it may sound like doing good data analysis is impossible, right? I'm not saying that. All I'm saying here is you should be conscious of these things, okay? It's unavoidable. In many cases, it's unavoidable in practice. We should always be conscious that if your final hypothesis is the result of trying multiple things, even in your mind or in your eye, then the effective VC dimension is larger than the final one you pick. Okay? All right. And finally, one of the most difficult to avoid data snooping, especially for discipline like economics, is that the data you're using is not new data. Okay? Now, you're not generating data from your own experiment. You are taking the data from somebody else. So for example, in economics, many data we use are publicly available data sets that everybody can analyze, right? We use observational data published by the government or has already been used by many, many people, and we're just using them again, right? You're all familiar with, I think majority of our data sets are publicly available that we can use. So what's the problem with that? Well, the problem is before seeing the data, you have already read many papers that do research using that data set. So you already know what models work for that data set, right? So when you jump in and use that data set to try to do analysis, you are going to pick some model. First of all, you are going to pick some model that's not going to be, right, people have not tried before, because otherwise what's the point? And the second, you already have some knowledge about what kind of model may work well. So you're going to pick your model based on that knowledge. So when you're doing that, even if you're not specifically doing any search, your final model, the VC dimension, should actually include all the previous models that people already tried on this data set, which is huge, okay? Which is huge. And that's called adaptive analysis sometimes, right? People call it adaptive analysis, but it's also a case of data snooping, right? Okay? When you're using a data set that has already been used by many people with many published studies, you already kind of know what kind of model would fit that specific data set well. And you go in and try to outperform everybody else, right? You try to give a model that generates better results than everybody else. So it's almost like there are many, many people who are trying. The first people try this model, the second people try this model, third people try this model. Everybody is trying on the same data set with the goal of finding better and a better and a better fit on that data set. So it's almost like we're trying harder and harder to fit a specific set of data. And in the end, the generalization ability will become worse and worse and worse. Right? And that's, unfortunately, that's a problem that's very hard to avoid. especially for discipline like economics, where we do not generate a lot of new data. Right? So in discipline like physics, natural science, right? Physics, biology, everybody generates their own new data by doing experiments. Right? Doing experiments, the data is all new, and you can do analysis on them. In economics, we are primarily not an experimental science today, right? We still use a lot of observational study. In fact, this course is about how to generate, analysis, how to do analysis on observational studies. So when we do that, and the observation study has already been used by many people, and you have read their research, then this is a serious problem that posing a threat to the validity or to the generalizability of the results in our economic science. And you can even understand this in this way. You can even think about this as the reason why economic models have not been performing very well, right? So, we all lament the fact that economics is not physics in the sense that our model do not perform as well, okay? Do not have the same predictive ability. Now, there are many reasons, right? But you can even think about this as one of the reasons why. Because we're always working on the same data set, and we're always trying to fit the same data set well and harming the generalizability of our model to predict the underlying population. Okay. All right, so what is the moral, right? Well, the moral is, first of all, always be aware of multiple testing and data snooping that might be going on behind the published results, and adjust your belief about them. Always be aware of the inherent data snooping problem when people are working on the same data set again and again, repeatedly, right? And one, a very good practice to follow, but perhaps not possible in economics, but very good practice to follow, is to always formulate your research and decide on your model before seeing the data, okay? Or before generating your data. This is very hard to do in economics, oftentimes not possible. But in other disciplines, okay, so this, if you're not an economics student, if you're in medical, if you're a medical student, biology student, that this is practice, this kind of advice is very important, because nowadays, in a lot of biological studies and medical studies, you have to, this is industry rule, that you have to pre-register your experiment. By pre-register means before you do your experiment, you have to specify how you're going to do your experiment and how you're going to analyze it, what kind of model you're going to run. And you have to pre-register it on the website, with the, for example, with the American U.S. Science Foundation, National Science Foundation, you have to register your clinical trial, and then you do your experiment, and then report your results in a published paper, in a paper submitted to the journal. So the reason why in these disciplines that editors nowadays demand you pre-register your trial is exactly to avoid the multiple testing problem, right? In economics, it's hard. We typically do not do that, but you should always be aware of that. Okay? All right, and finally, when reporting your research, aim for honesty and transparency, of course. Clearly state your research question, the research design, and the reasoning behind your model choice. Of course, also when you read other people's paper, you should always be aware of that. Do they have a clear reason for choosing the model they end up using? If they do not have a clear reason why, then maybe something is fishy, right? And even if you do some amount of data snooping, you should admit it, okay? And tell people that, look, I tried all these things, and this is my result. Okay? Don't hide behind. Report every test you have performed, rather than only report the final one that is significant. All right, so much. That's all I want to say about this topic. Largely on the use of p-values in actual research and how our publication industry sometimes leads to undesirable results. And finally, if you're interested, this is the ASA, American Statistical Association Statement on p-values, how to best understand and use p-values. And if you're interested, you can read through them. All right.